Hi everyone, this little PowerPoint is about how to plot a line graph. Okay, it's in relation to the osmosis in potato tissue experiment from National 5, but plotting a line graph is important for National 4, National 5, higher, advanced higher, all levels. And the thing with this experiment is it's probably the most complicated line graph you'll ever plot at National 5 level, okay, because it involves positive and negative numbers. So if you've been directed here from one of the National 5 e-learning lessons, you'll be familiar with the learning intentions and success criteria. We're now on the last bit, which is draw a line graph with negative and positive values. So if you've not been doing the e-learning lesson from the National 5 course, which is looking at osmosis in potato tissue, let me just tell you what's going on. Basically, we've got 3 different salt solutions here. We've got water, so no salt, and then a higher salt solution here with 5 grams per 100 mils, and then one in the middle. And basically, the pupils have put bits of potato in the 3 salt solutions, left overnight or left over 20 minutes, and they are trying to find out how that affects the potato. So they have calculated the percentage change in length, and then they did repeat this 3 times, so they've got their average. So we're at the point here of having our average percentage change in length of the potato for each salt solution, and we just need to graph that just now. Now, you might not have graph paper, so if you don't have graph paper, you can go to this website. There's many other websites for you to be able to download graph paper, and then you can print it off. Alternatively, if you've got your squared jotter for maths or something, you could use that. Graph paper is better, but that's fine as well. Now, before we start thinking about plotting a line graph, we're going to go over some of the rules first to get ourselves started. We need to follow these rules in order to get a good line graph. Now, before you begin, you will need graph paper, okay? You can't do it on any other paper other than squared paper I'd mentioned before. You need a pencil and a rubber and a ruler, okay? You need to get all these things ready. Don't do it in pen, because one of the most annoyingest things is when you nearly finish your graph and then you make a mistake, you have to start your graph again, okay? Right, going to go through the guidance here. Now, let's have a look at my graph paper. One of the rules for exams, for the SQA, is you must cover at least half the graph paper. So if I plan on using this whole graph paper for this graph, I need to have my graph at least, if it's going to start at the bottom, come up halfway and cover half of the graph paper. But to be honest, I'm probably going to use a lot more for this graph because we've got positive and negative values. Here's a little tip. If you're doing your assignment or you're going to be sticking a graph in something, you can just do your graph and then cut the graph out. But if you're actually in an exam and you get given a designated space, you must cover at least half of that, okay? With your axes and your plots. Point number 2, axes labeled. Because obviously you know you're going to have to label your axis. If we look at this diagram down here, we've got our y-axis here and our x-axis there. Now, when we talk about labels, I don't mean label at y and label at x. I mean use your results table, and wherever you are putting up your y-axis, you have the exact same words that's in the results table. If the results table says concentration of salt solution, you write concentration of salt solution. You don't write salt solution concentration, okay? And the other thing that you must have on your axis is your units. If you don't have your units, you're going to lose marks, because quite often you get a mark for the labels and the units. Really easy mark. If you've even plotted anything, you've got yourself marks. Then we're going to talk about the scales here. Now, when we talk about the scales, we're talking about the numbers that you put onto your axes. They must be regular. So if you look at the bottom, it's going up in 10. So 0, 10, 20, 30. It can't go 0, 5, 15, 45. It needs to go up in a regular interval. So that could be going up in 2s, 4s. You could even go up in 13s. But the point is you've actually got to go up in 13 every single time. Okay? So the same distance. So here is the same distance to there, and it indicates the same number of units. What's important though is you don't have to have the same scales on your x and y axis. In this graph here, they do. They both go up in 10s, but it's perfectly fine for your y-axis to go up in 5s and your x-axis to go up in 20s. That's fine. It really depends on the data you're looking at. Now, this one here says you must have an origin on each axis. Now, this has actually changed. You don't need an origin in each axis anymore, but it's very good practice. And basically, the origin tells you what you're starting at. So here, we've got two origins here, and they're both starting at 0. If you don't include an origin, you'll lose marks. So if they didn't have the 0 here, and they just went 10, 20, 30, you'd lose marks because the examiner was not going to know, well, did you start at 5, did you start at 0, did you start at minus 10? Okay, you must include your origin. Also, your origin doesn't need to start at 0. You could, if you're dealing with really high numbers, you could start your origin at 100. You could start it at 44. You could start it at whatever. But just remember, we still need to have our regular intervals. Okay? Next one, plotting your data. You must use crosses, okay? If you use dots, it's less accurate, because if we look at the cross, we know fine well that this, oh, here's my pen, that bit here is the middle. The centre of the cross is the middle, and that's where you've plotted it. That is the number you're talking about. Whereas if you've got this circle here, it might cover quite a lot of your graph paper, so it's just not as precise. Once you have got your crosses, and you've plotted your data, and I'll tell you how to do that, close to like when we're actually doing it, if you're not too sure, you then need to join up your crosses with a ruler. So you've used your ruler for drawing your axes, and you're now going to use your ruler for joining up your crosses. Now this is important because biology, chemistry and physics are all different. Biology, you're going to join up the centre of the cross, the first cross, to the centre of the next cross, to the centre of the third cross. And if you notice there, I did a little curve. That's because I wasn't using a ruler. That's not good. We must use rulers. Whereas if you're doing chemistry or physics, you might do something called a line of best fit. That's not for biology. Don't do it. You must join the dots. And you must start your line from your first data point. So my first data point is that first x. But what some people often do is I see people joining the first x. Now where are you? Oh gosh. There. Joining your first x to 0. Don't do that. No, no. You just start your line from your first data point, because you don't actually know what's happening if you had, I don't know, 0% whatever. You don't know what it is because you don't have your data for that. Now the task at hand is plotting a line graph of the average change in length against the salt solution concentration. This means we can completely and utterly ignore this data because we're only concerned with the averages. Okay. The next few slides are going to give us a few hints. So what I'd like you to do is pause this video every now and then for you to maybe try and do your own graph along with the hints. At the end of the hints, I'm going to draw the graph for you. It might not be in real time. I'll probably pause it whilst I write things in and stuff. But what I don't want you to do is just copy my graph. I'm just doing it at the end for those that are really, really struggling. I'm hoping some of you won't even bother watching that bit of the slides. Okay? So, line graph hint number 1. We've got positive and negative numbers. Sometimes the potato is increasing in length and sometimes it's decreasing in length. So our axes must reflect that. So what you can see here is our y-axis is very long and it's got the x-axis right in the middle. This means our positive numbers are going to be above 0 and our negative percentage changes are going to be below 0. Line graph hint number 2. Where are you going to put your axes titles? Now, remember we talked about independent and dependent variables earlier on in the e-learning lesson. The independent variable is the one that the experimenter controls. So, I have, as you did, have set out your salt solutions. You've made them and then you used them. So, the independent variable always goes on the x-axis, so your salt solution is going to go along the x-axis. The dependent variable, which is the one you're measuring to try and answer your aim, that goes on the y-axis. So we've got our average percentage change in potato length along the y-axis. A good way to try and remember the difference between the independent and the dependent variable is the dependent variable depends on the independent variable. So that's the thing that you'll be measuring. It's depending on something else. So hint number 3 is about scales. Remember, they must go up in regular intervals. Now your salt solutions were 0 grams per 100 ml, 1 gram per 100 ml, and 5 grams per 100 ml. But what you're not going to do is just go 0, 1, 5, okay? You need to have the regular intervals. Between 0 and 1 is 1 unit, but between 1 and 5 is 4 units, okay? So if you're doing regular intervals, they must be going up in our 1 unit. So you're going to include 2, 3, and 4. And it doesn't matter that you've not got data for that. You just don't put any X's or any crosses above those points. You'll just have it on the 0 line, the 1 line, and the 5 line. Now, a common mistake is people will put their 0 here, okay? That's not where your 0 is. Your 0 is actually on the y-axis. So you're going to put a cross, whatever you're meant to, up on the y-axis for your 0 salt solution. Now, in terms for scales for your y-axis, you need to work out what is the highest percentage increase. So what is the biggest positive number? I can't fully remember, but I think it was 25. So you're going to want your y-axis to go up to at least 25. I would maybe go to 30 because it's a nice round number, okay? And then you need to work out what's going to go down to. And I can't fully remember what the smallest number is, but I think it was about minus 23. So I would maybe go down to minus 25 or minus 30. So we know that we're going to be going up to plus 30. And just for argument's sake, we'll say negative 30. So to work out your scale, what you do is you count, because remember your graph paper is going to have squares in it, okay? Little squares in it. We'll have little squares and big squares and medium squares, okay? You need to count how many squares there are, and then say if there's 10 or maybe there's 20 or 30, and then you basically divide the difference, which is 60, okay, because we've got 30 up, 30 down, 60. You divide the number of squares by 60, and that'll tell you how many squares that'll be worth. So if you're using the big graph paper like this, you might find that when you've drawn your axis, there are 12 big boxes. So what you would then do, sorry, I don't have my scientific calculator, I've got my iPad. What you would then do is get your calculator up, and you would do, remember it's 60, between minus 30 and 30 is 60 units. You do 60 divided by 12 equals, I mean, some of you won't need to use a calculator for that, equals, oh, here we go, 5. That means every box is worth 5. So you're going to be going up in 5. So you're going to go 0, 5, 10, 15, 20. And then down the way it'd be negative 5, negative 10, negative 15. Okay? That's how you work out your regular scales. You might initially count your boxes and it says something like, you know, each box is going to be worth 3.33. That's going to be complicated, so you might want to edit the size of your graph, alter the size of your graph. But you've got your trusty rubber here, so it's easy to do. Right, I'm now going to draw our outline graph. I'm going to show you it step by step so that you can work along if you need to. Okay? I'm going to pause it every now and then for you to fill in because it's going to be very boring if I just record me drawing it all. I am, however, going to not follow one of the rules, which is use a pencil, because it's going to be harder for you to see. I'm going to use a black felt tip pen. If any of you use a black felt tip pen, I'll be very irritated because you have to use a pencil. So, step 1, draw your axes. Get in my ruler and my pen, or pencil, and I already know we're going to have positives and negatives because I've got my data here. I know that there's positive numbers and I know that there's negative numbers. And I also know that my average percentage change will be on the y-axis because it's the dependent variable, and my salt solution will be on the x-axis. Here. Okay, so it should look a little bit like this. I'm now going to do my scales. I'm going to do the x-axis first because it is pretty easy, okay, because we've only got 5 numbers. In the last slide, we went up in ones. I might decide to go up, well, still go up in ones, but maybe use more than one square because I've got all this space. There's only 5 numbers. So I've done it like this. I've used the big square for every 1 unit. Now I should explain this because sometimes it's quite hard to see. I've got the graph paper where I think it's quite easy to see, but you see that we've got big squares. Oh, see, that's why I was going to move the ruler. You don't use a ruler. Big squares that are made up of 1, 2, 3, 4 smaller squares. And the reason you can see these is because we've got bold lines for the big squares, which are here, you know, these bold lines there. And then we've also got bold lines for the little squares as well. Now, inside the small squares, you've got even smaller squares. So, for every big square, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 small squares up and along. Okay. For the medium-sized squares, so the 4 inside the big one, it is 5 little squares up and 5 little squares along. And then we've got our smallest squares, which are the wee teeny ones, which are just like that. The reason I'm showing you this is because I want to point out the coloration of the line. When you're doing your scales, make sure you're using the bolder, thicker lines because that makes it much easier to count. So it makes it much easier to see your big squares. If you were to start your axis on a non-bold line, you'd then have to physically count 10 little squares for every place that you place a marker, which is really annoying. Whereas if you make sure you draw your lines on the bold lines, then you just go to the next bold line. Okay, simple. So now for the y-axis scales. Now, if you look at the size of my line, when I go and count how many big squares, the big squares, I go from the bottom. So I go 0, 1, 2, 3, 4, 5, 6. Up to 0, 1, 2, 3, 4, 5, 6, 7. Okay, so I've actually got one extra up in here, up on the positives. Doesn't really matter. So I've got 13 big boxes. I'm actually going to go to 12, it's an even number. And if we look here, our biggest number is 23.8. So we'll make that like 24 in our heads for doing this. And our smallest number is negative 26.2. Okay, so I'm going to, with my original idea, I'm going to go up to 30 and down to negative 30. And remember what I did is I basically had the 60 units because there's 30 here, there's 30 there, so that's 60 altogether. And I divided it by how many squares it had, which was 12. So 60 divided by 12 is 5. So that means I'm going to go up in 5s. And I'm going to use my big squares. So it's going to go 0, 5, 10. 0, negative 5, negative 10. And this is what you should have now. So I've got my 2 axes, I've got my 2 scales, they're regular intervals. Now I don't have labels yet. I like to put labels on at the end because we need to see where the x's are going to go and we don't want to be writing over the x's or anything. So I'm going to wait to the end before I put my labels in. So now what's left to do is to plot our actual data. So for the actual plotting of the data, you need to work out what every little tiny box, let me use my pointing pencil, every little tiny box is going to be. So if between the numbers 0 and 5 are 10 little boxes, that means every little box is going to be 0.5 because 5 divided by 10 is 0.5. Okay, it would, if it was, if our 5 was here, that would mean every little box was worth 1. But because for every single unit we need 2 boxes, so it would be 1, 2, 3. Every little box is worth 0.5. Now, if we look at our numbers here, we've got 23.8, 1.6, 26.2. That's going to be difficult to plot if our smallest box is 0.5. I mean, we can make a rough guess because remember, you can go halfway in little boxes. So if it was 0.75 you were plotting, you would just go up 1.5 boxes. However, we're looking at 0.8 and 0.6 and 0.2. So it might be easier, and for argument's sake just now, I'm just going to round these. So plus 23.8 is going to turn into 24. Because remember, when we're rounding, if it's above if it's 0.5 or above, we round to the number higher. And if it's less than 0.5, we round it down. So our 1.6 will become 2, but our 26.2 is going to remain at 26. Okay, sorry for my horrible writing with this pen. Obviously, you'd be doing this much neater. And you could actually, if you really wanted to properly do it right, you would add another column onto your results table, again using a ruler so you don't have this weird shape, and you'd call it rounded average percentage change in length. And all of these numbers would be put into there. Okay? So now we're at the point of putting our crosses, so actually plotting our data. So, data number 1, we'll get a different colour pencil. For the 0% salt solution, it is 24. Okay, so what we'll do here is first you go along your x-axis to the number you need. Our x-axis number is 0, so we don't go along, we start it here. So 0, and then we've got to go all the way up to 24. Now, 25's there, and if we know that every tiny box is worth half a unit, that means 24 is going to be 2 tiny boxes under 25. And you're going to put your cross there. I'm going to get my black pen to show you. But I did it in pencil first because I didn't quite trust my accuracy. And I didn't want to have to start again. Okay? So now I've gone over it in black pen. So there is my first X. Now my second one, we are looking at the 1 gram per 100 mils. And we're going to go up to 2. So we're going to go along to 1, and then we're going to go up to 2. But remember, 2's not written there, so we're going to have to work out what it is. So if every little box is worth a half, we're going to go half, 1, 1.5, 2. So I'm going to have to go up 4 tiny little boxes. So, there. Okay. Now we're on to, and notice I'm going to skip 2, 3, 4. We don't have data for that, so there's going to be no X's up or below that. We're going to go to our 5 grams per 100 mils. Okay, and we're going to go down to minus 26. So same thing again. Go along to 5. We're going to follow that line down all the way down to minus 26. Now remember, we've not written minus 26. We've got minus 25. So it's going to be 2 small boxes, because every box is worth a half. 2 small boxes past our minus 25. Now, let me do that. Right. Oh, there we go. So we've got one cross all the way up here, and then our other cross all the way down there. So now we've got our crosses, we've plotted our data. What we have to do now is join up the dots. Okay, using my trusty ruler, I'm going to go to the center of one cross and join it to the center of the next cross in order. Okay, so it's going to go from the 0 to the 1, and then the 1 cross is going to go straight over to the 5 cross. And my graph looks like this. Yay! However, I have not finished because I need to put my labels in. Now, I'm going to take them word for word, exactly what the results table says. So, my x-axis is salt solution. I'm going to write it in full because the table's in full. I'm not going to write salt soln, which is a abbreviation. I'm going to write it in full. Salt solution. Then I'm going to pop my units in, grams per 100 mils. Then I'm going to look at my y-axis. And it is average percentage change in length. Okay, and it's although I've got the units in the title, like, you know, it says percentage there, I'm just going to put my units in brackets again, just to cover my back, just so that nobody can argue I didn't do units. So I've got my label, my units, my label, my units. I've got regular scales going down in 5s, going up in 5s, going along in 1s. I've got my X's. You will have used a pencil, so you've done that one, and I've used a ruler to join up my dots. That's it. That's my line graph. You don't need a title. I think maths needs a title, but you don't need a title. But for neatness' sake, you could do a title, especially because our y-axis doesn't mention the word potato. So you'd probably want to put a wee title talking about potato. So let's call this average change in length of potato versus salt solution. So then we make it really clear what we're actually doing. Next thing you'll want to consider is, once you've got your graph, what does your graph actually show? Well, when we have a low salt solution, so 0, we have a high increase in potato length. When we have a high salt solution, we have a low increase in potato length. So what you could say is, the higher the salt solution, the greater decrease in length of potato. Or, the higher the concentration of water, the greater increase in the length of potato. Now, if we, just to add this in, if we had a salt solution that was here, which would be 1.3 grams of salt per 100 mils, we can predict that we would have no change in the size of the potato, which would indicate that there was the same amount of water going into the potato as going out, so it was balanced. So we could say that the potato has got a concentration of 1.3 grams of salt inside it. Okay, that's one of the sorts of things we can do when we look at these graphs. Where it passes no change, no percentage change, that will indicate how much salt or water is inside the potato, because it's going to be equal to that solution because there's been no osmotic change. So that brings us to the end. You should have a nice line graph. Now what you can do, if you were doing your line graph before watching the video of me doing your line graph, just skip to the very end of my line graph to see if it looks the same. But what's really important is that you now take a picture of your results table and your line graph and send it to your teachers. Now this has been given to you on Teams via an assignment, so when you click submit on the assignment, you can actually attach a document. So if you take a picture of your graph and your results table and attach that onto your assignment and then press submit, we're going to be able to look at it and give you feedback. Okay? But that's us finished today, because we have drawn a line graph with negative and positive values.